Hi! Halogen lamps are known for being more efficient than ordinary incandescent lamps, giving more light per watt. But I find that counterintuitive, since halogen lamps are running hotter. Making more heat seems less efficient. In this video, we'll take a closer look at what makes halogen lamps special, the halogen cycle, and why running hotter is more efficient in this case. There is, however, a limit to how hot they can run and still have a reasonable lifetime. Try guessing how few hours this small 1000 watt halogen lamp running at 3130 degrees C or around 5666 degrees Fahrenheit is expected to run. Let's find out. Don't toast yourself on hot lamps, and don't handle the nasty halogen elements. The filament in an ordinary incandescent lamp runs at around 2700 kelvins, twice as hot as the hottest lava. Running it hotter would shorten the lifetime of the tungsten filaments, since it would evaporate faster. Halogen incandescent lamps also use tungsten filaments, but often do run much hotter. This 28 watts halogen runs at 2900 K. So does this 120 watts halogen. Going much higher in wattage, this 500 watts one cooks at 3000 kelvins. This 800 watter is a scorching 3100 K, and this 1000 watt halogen is burning at 3200 kelvins. Or how about a 1000 watts at 3400 K? That's hellish hot. Why would they run them that hot? Well, in my previous video, where I measured the temperature of my toaster without a thermometer, I showed Planck's law. This equation can be used to estimate the spectrum and intensity of light coming from anything hot enough to glow. If I plot the theoretical blackbody radiation from an incandescent filament running at a typical 2700 kelvins and a hotter halogen filament running at, say, 3200 kelvins, the difference is striking. The 3200K is more than double as intense in the peak, and much more of the radiation is visible light. The 3200K is simply much brighter, emitting way more light visible to us. That's the quantum mechanical effect of electrons that makes halogen lamps more efficient. Running at higher temperatures make them glow brighter, turning more electricity into visible light. But why is the tungsten wire not evaporating fast at temperatures well over 2700 K in a halogen lamp? This is where the halogen regenerative cycle makes a difference. At the very high temperature of the filaments in any incandescent lamp, tungsten will evaporate even though the temperature is well below tungsten's boiling point. This kind of evaporation is called sublimation. The tungsten goes directly from a solid to a gas without melting and boiling, simply because the tungsten atoms vibrate fiercely at the high temperatures, sometimes enough to break free of the filament. In an ordinary incandescent lamp, this vaporized tungsten will mostly condense on the coldest surface available, the inside of the lamp's glass envelope. This slow flow of tungsten from filament to glass will thin the filaments until it burns over. But in halogen lamps, some smart chemistry opposes this flow by adding one of the halogens. The halogens are all rather nasty elements. Here is iodine, also known as iodine. It is hard to keep trapped and will stain most things in its path. Iodine was used in early versions of halogen lamps, but modern versions mostly use bromine, which is even worse. Luckily, my sample is in a sealed glass ampule. They don't add elemental bromine like this to halogen lamps. Often a gas called hydrogen bromide or other bromine compounds are added. These halogen compounds break down at a high temperature. The trick is that the free halogen atoms then chemically react with the evaporated tungsten and trace amounts of oxygen added to the high-pressure gas inside the halogen lamp, forming tungsten oxyhalides, tungsten oxybromides in the case of bromine. When these oxyhalides are carried back to the filaments by convection, the immense heat breaks up the molecules and the free tungsten is deposited back onto the filaments. This clever cycle reuses the evaporated tungsten. Halogen lamps can therefore run hotter, despite more tungsten evaporation. But the halogen cycle is not perfect. These lamps will not run forever from recycling the tungsten equally over the entire filament. After a short message, I will reveal the expected lifetimes of these lamps, including that extreme 1000 water. A huge thank you to all my patrons. Thank you so much for helping out. It's really appreciated and important for a niche channel with monthly quality uploads like mine. For just $1 a month, you can help me out too and get full access to all my posts on patreon.com. Link to my Patreon page in the description. Thank you. Here are some expected lifetimes for the halogen lamps. For the 800 water, the higher temperature is starting to have an effect. But going 200 watts higher in the same bulb size, to 1000 watts running at 3200 K, the lifetime really drops dramatically. This 1000 watts halogen will last 50 hours. 50. 2 days, give or take a few hours. Even shorter if you turn it off before the glass gets hot enough for the halogen cycle to start working. Yeah, the halogen cycle is struggling to keep up when the filament is evaporating at 3200 kelvins in such a small form factor. In a larger lamp format, like the one I have unboxed earlier to my patrons, a 3200K filament can last for 400 hours. But at even higher temps, it gets worse yet. This 1000 water from the intro runs at a stupendous 3400K for max light output and likely stronger blue colors in projectors as well, giving it a stupid lifetime of 15 hours. No, not 50 this time. 15. Kind of a flashbulb. Don't forget to turn this one off when you leave the room. The hottest halogen I have is a Philips 3450K projector lamp that will last an almost impressive 50 hours. Comment if you know of a hotter running halogen. Temperature is, however, not the only factor that determines light output and lifetime. Take a close look at these two very similar light bulbs. Same voltage, same wattage, same color temperature. But one will last 10 times longer than the other. What makes them this different? Well, one is tuned to a light output of 3900 lumens. The other, short-lived one, a massive 5000 lumens from the same watts. Placed side by side, it is clear they are not built the same. The long-lasting one has a longer, thicker filament and a larger glass envelope with more gas. I couldn't help but measure their resistance. Are they really the exact same? Note that tungsten's resistance will increase significantly with temperature. But this resistance measured at room temp also includes the pins, lead wires and molybdenum ribbons that will not heat nearly as much under use. At the precision I can measure with, yes, they are the same and therefore same wattage. Just tuned very differently for lumens or lifetime. Designing an incandescent filament is not a trivial compromise. Finally, I should mention that LEDs are not incandescent. Color temperatures of white LEDs do not say anything about their actual working temperature. It's just a comparison to how hot an incandescent light would have to run to match the LED's color temp. In a recent video on Patreon, open to free members, I tested 2 grow lights with high 4000K and 5000K color temps. Their spectrums are not quite as advertised. Hope you enjoyed this video enough to click like and perhaps subscribe for more like it. In any case, thanks for watching. Bye for now.